All right. So um, today we're going to look at, we've been looking at hypothesis testing. We've been looking at if you have a model of the world, how to make predictions and how to compare that to what you observe. And today we're going to talk a little bit more about how to make principled decisions about whether you should believe in your model or not. Okay, so we talked about hypothesis tests and p-values on Monday. Today, we're going to talk about how to make decisions using the information from hypothesis tests. And part of what we're doing is we're getting a little bit comfortable here with the fact that we are not going to have a definitive answer. We're going to have to either proceed by assuming that our model is true or assuming our model is wrong, and we're never going to know for sure if we were right. So it's about making the best decision we can when we don't have all the information. And then Friday, we will look at, we didn't talk about p-values. Thank you. Sorry, I missed lecture on Monday. Okay, then I will talk about p-values today. You will learn about what p-values are. And then Friday, you'll learn about some applications of this called A/B testing, which is used, for instance, in marketing to test different variants of a web page or ad to see which is most effective. Newspapers do this on you all the time. They try multiple different headlines and see which ones cause people to click the most. Okay, so announcements. Group office hours are canceled. I'm sorry if you're going to group office hours. Instead, attend regular office hours, sign up for the queue, select conceptual, or you're all invited to attend my office hours, which are Wednesdays right after class at noon. We're gonna run some catch-up sessions. Are you feeling a little bit lost or struggling to keep up, or maybe there was a topic that you just didn't quite get? We want to help you prepare for the midterm by holding some extra reviews catch-up sessions where you can get some practice. If you're interested in that, answer this poll about which topics you'd most like us to do, and we'll run a few of these before the midterm. Homework 6 is due tomorrow. Don't forget. And homework 7, we know the midterm's coming up. You're going to be thinking about the midterm. We want to give you a chance to get started early on the homework. So we're going to release homework 7 later today. It's a little long. It's designed to give you a lot of practice. It's kind of long. You may want to start early. It'll be due, as usual, next Thursday. Midterm reminder, a week from Friday. Start thinking about it. We'll tell you more about what to expect from the midterm, but I would expect the format to be pretty similar. I'm still writing it right now. It's going to be quite similar to what you've seen from past semesters, and we'll give you details soon. All right, so let's talk about today's topic. I don't have a lot more to tell you about the midterm. We'll have the information for you soon. All right, so in this hypothesis testing segment, what's going on is we have two different models, two different views about how the world might work. And we're trying to choose between them. Okay, so we're trying to figure out which is how the world actually works. And we're trying to use data to draw some inferences about how the world works. Doing the best we can with the data we got. Okay. Now, I just want you to be prepared that you may not always know the answer. Everything's not always clear. So we need some systematic procedure to help us make the most informed decision we can from the data. We've looked at some examples where when you look at the data, it's really evident just staring at the data that either everything looks consistent with the model or everything looks inconsistent with the model. It's not always going to be quite so clear cut. So we need a systematic procedure here. And the thing that I want you to keep in your mind here is that when the thing that makes this tricky is our models are going to make predictions about what we expect to observe if the model's true. But in data science, the tricky bit is that those predictions often have some randomness in it. So in physics, the prediction might be like, if you drop a bowling ball from this height, then it's going to take exactly 4.3 seconds to fall. And there's not a lot of randomness there. It's basically 4.3 seconds. And any deviation from that, maybe there's measurement error, but in principle, you can calculate exactly what's predicted by your model. In the scenarios we're looking at here, that's not the case. The prediction is not 4.3 seconds. The prediction is it's random how long it'll take. And there's some distribution that might be centered at 4.3, but it might be more than 4 or less than 4. So we're going to need a way when we observe something like 4.5 to say, well, was that consistent with the predictions that were made by our model or not? Okay. Because it's random, there could always be a chance of happening to choose a really bad random sample that gives you a really unlikely, unusual value. It's possible. It's just not very likely. All right. So there's always going to be the possibility that we make a bad decision because we get an extremely unusual outcome and we say, oh, that's really unlikely. But coincidences can happen. They're just kind of rare. All right, so terminology. Hopefully you've seen a bunch of this terminology before. Stop me if there's any of this you haven't seen before. What we're doing is called hypothesis testing because we're testing two hypotheses. So this test chooses between two views of the world, two models for how data were generated. And these models or these views are called hypotheses. They're like a theory or a model or an explanation that we might tentatively hold or we might put out as possible. So we have two hypotheses, and the hypothesis test picks one of these two hypotheses. You can sort of think of it as like trying to choose which one seems to be consistent or fit with the observed data. And the names we call these, there's standard names for these hypotheses in the statistics literature. And so we're just going to go with that. They're a little weird, but this is the convention, so we go with it. It's called the null hypothesis and the alternative hypothesis. Okay. And so we're selecting between the null hypothesis seem to be correct, or is the alternative hypothesis seem to be correct? The methods that we're showing you here are only going to work if you can simulate the outcomes that would occur if the null hypothesis was true. So one of these two hypotheses has to be well enough specified that you can simulate what will happen if that hypothesis is true. And that one we call the null hypothesis. The hypothesis you can simulate, we call that the null hypothesis. And the null hypothesis often tends to be something like, there's nothing more happening here other than random chance. I'm flipping this coin and this coin is fair and it's just random whether it comes up heads or tails. And the alternative hypothesis is often the one that says, well, there's something else happening other than just chance. Okay. So the null hypothesis is a well-defined model, a chance model. There's some chances involved about how the data were generated. So it's fully specified. Like all the probabilities are fully specified by the null hypothesis. If there's some sampling, it's fully specified, like is it with replacement or without replacement? That whole process is completely described by the null hypothesis. That is what enables us to simulate outcomes, simulate what kind of data we would see if this model were correct, if the null hypothesis is true. And often what we'll say, just kind of shorten that, is under the null hypothesis. Under the null means assuming that the null hypothesis is a correct statement of how the world works. Where does the term null come from? Null, I don't know. It's convention. The null hypothesis usually means boring, nothing happening here. It's kind of the baseline. So null would be like, if the null hypothesis is true, it's like there's nothing happening. It's called a null result. No effect of the treatment. That's common kind of association there. The alternative hypothesis is the other one. And typically the alternative hypothesis will say like, well, the null isn't true. That would be an example of an alternative hypothesis. Or another example of an alternative hypothesis would be, the treatment does have a beneficial effect. Okay, so the alternative hypothesis is a different view of the world, and often it's not fully specified. So the null hypothesis might say the treatment has no effect. Your outcomes are random. And the alternative might say the treatment does have an effect. Maybe it says it does have a beneficial effect, but it's not fully specified because the alternative doesn't say how much effect it has. It just says it has some amount, we're not sure how much. Okay. And then the null hypothesis is helping us trying to decide between whether we should proceed based on the assumption that the null hypothesis is true or the alternative hypothesis is not. Like in the future, should we give people this treatment? Okay. Um, um, great, great points here. I see comments in the chat that are pointing out that you got to prepare yourself that we're not going to have a definitive answer. Maybe we may not have a definitive answer that definitely the null hypothesis is correct or definitely alternative hypothesis is correct. We're going to have to be forced to deal with some uncertainty. That we're going to have to make a decision. We're going to make the best decision we can, but we're not really going to know for sure if we're making the right one. So we're going to use the data to give us some evidence to help us select which seems like a better choice. And the data might help us reject the null hypothesis. And then if the null hypothesis is not true, then we would be natural to conclude that the alternative is true and proceed on that basis. Or alternatively, the data might be consistent with the null hypothesis, and then we can't reject the null hypothesis, and the null could be true. The alternative could also be true. Note, model and hypothesis are just two different names for the same thing. If you're a statistician doing hypothesis testing, you call it a hypothesis. If you're a scientist who is constructing some physical theory of the universe, you call it a theory or a model, and we all mean the same thing by that word. Just kind of historical anachronism, which words you happen to use. All right, so now to help us make this decision, we're going to have a test statistic. And a test statistic is a way of summarizing all the data. So we draw some observations, we get a whole bunch of data, and now we're going to try to summarize that with a single number. And that number is called the statistic. Okay, so the statistic depends on the observed data. And that's some function of the observed data. And here's where the art of the hypothesis testing comes in. You get to choose what to use as your statistic. There are some common patterns that are often useful in different situations, but there's no hard and fast rule. All right, so you're gonna have to choose a statistic, and hopefully this number that's gonna help you decide between the null and the alternative. So when you choose it, you should choose a number that you think is gonna help you. And by say help you, what I mean by that is you could think about what values of the statistic would tend to be like, would tend to make you think that the null was true, and what values would tend to make you think the alternative is true. Like if the null was true, maybe that would lead to observed data with a value of the statistic that is smaller. And if the alternative was true, that would tend to lead to values of the statistic that are larger. And if so, that'd be a useful statistic, because smaller values of the statistic would make you lean more towards the null, and larger would make you lean more towards the alternative. Okay, so like maybe your statistic is how long do the patients live after we give them this treatment or we don't give them this treatment. And then, we have some experimental treatment. And so now if maybe the statistic is, actually I should revise that. Maybe what we would use is the gap between the average time to live for those who got the treatment minus those who didn't get the treatment. If our null hypothesis says the treatment has no effect, then you'd expect there's not much difference between those two populations. Your statistic will be a small number like 0. If the treatment is great and cures people, then the people who got the treatment should live longer, and that statistic will be large. So that would be a useful statistic, because small values could be viewed as evidence for the null, and large could be viewed as evidence for the alternative. Now, how small and how large is a topic we're going to get to, but that's what we're looking for from a statistic. So when you're evaluating statistic, ask you what values would make you just intuitively tend to lean towards the null, and which ones would make you lean towards the alternative. And what we want the goal we're shooting for is that high values should make you lean towards the alternative and low towards the null. That's good. That's good. We want these kind of be a linear order between null on one end and alternative on the other end. What we want to avoid is a situation where you said, well, if it's really big or if it's really small, then I lean towards the alternative. But if it's in the middle, then I lean towards the null. No, not a good statistic. Don't use a statistic like that. Choose some different statistic. Okay. Whew. I'm going to keep going. All right. I know this is a lot. So just remind ourselves what we're trying to do. What we're trying to do is we're trying to compare the actual observations from the real world to our predictions. This is how we're going to decide whether we think the null hypothesis is true or not. The null hypothesis makes some predictions. And then, like any good scientist, we're going to compare the actual observations against the predictions. And if the observations are consistent with the predictions, then that's consistent with the idea that the null hypothesis could be correct. And if the observations are inconsistent with the predictions, then that we've refuted the null hypothesis. That's evidence that the null hypothesis probably isn't correct. All right, so how are we going to make our predictions? Well, in physics, making a prediction is easy. It says if you drop a bowling ball from this height, here's how long it'll take. You like have some formula that says the effect of gravity, and you plug in, you get a prediction. And that's what they're teaching you in physics, is like how to make those predictions and with what formulas are appropriate and all that stuff. But here in data science, we need a different method for making predictions. And we have the null hypothesis. The model now is a chance model. It's a randomized model. There's some randomness involved. But as I said before, the null hypothesis you need to choose so that it can be simulated. It's a fully specified chance model. So what that means is that we can simulate the null hypothesis. We can simulate what would happen if this model is correct. And that simulation will give us a possible outcome. And we can repeat simulating many times and we'll get many possible outcomes. And so that will give us a sense of what kinds of outcomes could plausibly occur. We're going to then summarize each of those outcomes using the statistic. So we're going to look at the value of the statistic you'd get for each of those samples. And we're going to look at the empirical distribution of those numbers. Okay. And the way we're going to do that is we're going to draw a histogram of those simulated values of the statistic that were obtained with a simulation that assumes the null hypothesis is true. We don't know whether the null hypothesis is actually true in the real world or not. So for the moment, we're just assuming it's true and seeing what predictions it's make. And the prediction it's going to make is a distribution. We're going to obtain a distribution on values of the test statistic. That's the distribution that should occur if the null hypothesis is actually valid. All right, so we call it the empirical distribution of the statistic under the null hypothesis. That's our prediction. All right. From that histogram, you can tell what values of the statistic are reasonably likely to occur if the null hypothesis is true. If your histogram looks something like this, you can kind of look at this range here of values that it would typically occur. And that's a range. You can think of that prediction as more or less a range of values that could plausibly occur. But it also tells us how likely are they to occur. All right. Now, once we have a prediction, then we're ready to use that to make a decision. We compare the observed value to this prediction, to this range of plausible values that we would expect if the null hypothesis were true. All right. And that now helps us make our final conclusion, make our decision. So we compare the observed value of the test statistic on the observed data to its distribution under the null, the distribution that would occur if the null hypothesis were true. We checked for consistency, all right? So by consistency, I mean we look at where in this distribution the observed value falls. If we obtain a value that's very unlikely if the null were true, then we say, I'm now suspicious that maybe the null is not correct. For instance, if I pulled out a coin and I started flipping it in front of you and I flipped it 20 times and every time I got heads, you might start to become suspicious that this is not a fair coin, or I learned a little trick for how to flip it. But in any case, it's not a random choice happening there. It could be that's a fair coin, and I just happened to get all 20 of them heads. But the chances that you can calculate are about a 1 in a million. So in that situation, you could be thinking, well, either like a 1 in a million chance coincidence just happened, or that coin is not fair. Which bet do you want to go with? I know what bet I would go with. It seems much more likely that I'm having you on and I got a two-sided, a coin that is head on both sides or something like that. That seems more plausible than that a 1 in a million coincidence just happened. All right. So if you saw me do that, then you'd probably conclude, I don't think that coin is fair, and I'm not taking any bets with you using that coin. You wouldn't know for sure, but it'd be a pretty reasonable conclusion. And that's what we're doing with null hypothesis testing. That would be an example where the observed outcome, 20 heads, is not consistent with the predictions that would be made by a fair coin flip. So same thing here in null hypothesis testing. If the observation is not consistent, if it's something that would require you to believe in a big coincidence to have happened, for you to believe both the null hypothesis to be true and that the observation happened, you'd have to believe in a big coincidence, then that's evidence against the null. And it would be reasonable to reject the null hypothesis and proceed on the basis that, the null doesn't seem right. All right, so in that case, we say we reject the null, or the data is more consistent with the alternative. And the way we're going to test whether a value is consistent with the distribution is we'll look at this histogram, we'll see where the data falls, and then I'm going to show you in this lecture how to get a more systematic way to tell if it's not entirely clear. All right, so in that example of coin flipping, yes, the null hypothesis was the coin is fair, which is a perfect 50-50 distribution. What is the null in any specific situation will depend on that situation. It might be perfect 50-50, or it might be something else. With Mendel's pea flowers, the null hypothesis was that 75% would be purple and 25% would be white. So 75-25 instead of 50-50. But it was still that every flower is chosen randomly, independently, exactly following this model. So it was a fully specified chance model. All right. Let me now pause for questions before I move on. I see a few. One question is, what's the difference between the observed test statistic and the simulated values under the null? All right. The observed test statistic is we go out in the world, we raise some pea plants in the garden, and we count how many have purple flowers. That's the observation of what happened in the real world. The simulated values under the null are our predictions. We imagine a universe where the null is true. Is that the world we live in, or we don't know? Maybe yes, maybe no. But in that imaginary universe, we then simulate what would happen. We grow some simulated flowers and we count how many are purple in that simulated universe. So that's the difference. It's the difference between the observation and the prediction. The prediction, of course, is a prediction that's made under the assumption that the null is true. So let's just assume for the moment the null is true and see what prediction we get. And then we're going to compare the observation to that prediction. And that's going to help us tell whether or not we think the null could plausibly be true. Is the observed test statistic given to us? Yes, usually you'll have some data. The point of a hypothesis test is you've collected some data, and now you want to use that to draw inferences about how the world works. Which of these two models is correct? So the observed test statistic is something we compute from the observed data. What if you have multiple observed values? Usually you will. You'll have a whole bunch of observations. You grew 100 pea plants in the garden, so you have 100 observations. And so now you need to summarize that with a single number, and that's what a statistic does for you. In the pea plant thing, we used what proportion of the plants had purple flowers. So that was the way we turned those 100 observations into a single number. So we always got to convert everything into a single number, and that's that's what the statistic does for us. The t-test. If you've taken another statistics class, you might see a t-test, and that's another form of hypothesis test. And we don't teach that in this class because it has some restrictive assumptions. under when, sometimes you can use the t-test, sometimes you can't. The approach we're teaching you in this class, you can always use. How do you see consistency in the histogram? I'll show you an example. We'll see. All right, let's move on. Let's keep going. All right, so I got another example for you here. This one is taken from a real situation where it was a large stats class that had 12 discussion sections. And each discussion section was led by a GSI, the teaching assistant. And then they took a midterm. And it turns out the students in one of the sections noticed that their average score on the midterm was lower than the averages in all the other discussion sections. And they came to the professor and they complained and they said, I think my discussion GSI is no good. The average score in our section is way low. All right, so let's go look at some data. Here's some data, and let's look at this situation and see how we're gonna what the professor should do. I'm going to share a different screen here. All right, so we've got midterm scores here. And I'm going to read them into the notebook. And there were, I don't know, 360 students in this class, and here are their midterm scores. And each row represents one student and which discussion section they were in and what their midterm score was. Okay, so let's just look at midterm scores by section. And you can see here are all the sections. There are 12 sections. We can see, whoa, what does this show me? This isn't quite what I wanted. This shows me how many students were in each section. So about 30 in each section. Oops, not what I wanted. I want to know the average score, average midterm score within each section. All right, so let's do that. And now we can see here, you know what, let me write it like this, just to be a little clearer. We are using an aggregation function. We're taking the average. So the average midterm score in section 1 among all the students in section 1 was 15.6. The average midterm score for all the students in section 2 was 15.1, and so on. All right, so you can see here the averages are pretty similar for all these sections. Well, the students in section 5 had a little bit higher average, and the students in section 3 had a little bit lower average. So you can see why the students in section 3 were a little upset, or why they were concerned. Their average was lower than everyone else, only a 13.6. All right, whereas let's see what the average of all of the class was. 15.49. So they were like almost 2 points below the class average. All right, so we're going to set up a hypothesis test. We're going to set up a hypothesis test to see whether or not these students really in this section really are doing significantly worse. And I see a comment here in the chat that says, it doesn't look too far off. I'm skeptical. All right. Good. So like I said, situation is not always going to be super clear cut. We need a methodology for what to do when things are not clear. All right. So here's the situation. Here's how we're going to set this up as a hypothesis test. Students came to the professor and complained. The GSI's response was to say, look, this could be just random chance. This is the kind of thing that happens through sheer chance, that if you have 12 sections, some section is going to have an average that's lower than all the other sections. There's always going to be one. Some sections are going to have an average that's a little higher, some that's a little lower. Not even if all GSIs have exactly the same teaching ability, just from sheer chance, there's a little bit of randomness, and what scores people happen to get, whether they were having a good day or a bad day, which students got assigned to which section. And the GSI says, this can be completely explained by the randomness. It has nothing to do with my teaching ability. So don't blame me. All right. So we're going to call that the null hypothesis. And the null hypothesis is going to say that scores have no relationship to the section you're in. That there's some distribution on scores, and every student gets a score from that distribution that's unrelated to what section they were in. The alternative hypothesis is no, there's something about this section that's not working right. The average score in that section was lower than can be explained by chance. It's not just randomness. There's something more going on. Maybe things weren't working well in that section. Maybe that GSI needs a little more help in how to teach. Maybe there's something else happening at that time. I don't know. All right, so that's the hypothesis test. And you're now gonna put yourself in the shoes of the professor who needs to make a decision between these two views of the world, these two hypotheses, the null hypothesis and the alternative hypothesis. So we're gonna see how we would help you make an informed decision. Okay. So let's continue working through the data and see where we can get. Here we go. All right. So what we need is we need a test statistic to help us. Can anyone type in the chat and suggest a test statistic that you think would help you choose between the null and the alternative? That should be a way to compute a single number from the observed data. In this case, the observed data are the scores of all the students in section 3. All right. Oh, yes. I love it. Lots of great suggestions here. Okay. I'm seeing a few suggestions here. I see 3 of them. One of them is the average score of the students in that section. Another is the difference between that average and the overall class average. And the third suggestion that I see really commonly is the absolute value of those. How should I choose between those 3? Well, the criteria are that we want, maybe I should pull up for you what's the null and the alternative. Sorry to flip back and forth here. All right, we're going to find a better way to do this. Here we go. Nope. Here. All right, here's the null and here's the alternative. The alternative says that the students in this section did worse than you would expect by average. So the absolute value is not what I would suggest here. Because if the observed value, the average in this section was higher than 15.7, it was like 16 or 17, that does not make me think the alternative is right. Okay, so lower values of the average of score for section 3, the lower it is, the more I'm inclined to think the alternative is true. The higher it is, the more I'm inclined to think the null hypothesis is true. So the absolute value is not a reasonable one to use here. The other 2 suggestions that I heard commonly are reasonable. You could use the average score within section 3. That'd be reasonable. Lower values suggest the alternative, larger values suggest the null. Or you could use the difference between the score in section 3 minus the overall class average, or the difference the other way around, the class average minus the score in section 3. Those would be reasonable choices. All right, so let's decide which one we're going to do. Let's see. I think what I prepared was using the average score in section 3 as my statistic. Don't have to use that. We could use a different one, but let's go with that. All right, so what we need now is we need a way to simulate the null hypothesis. So let's look at how to do that. I want to simulate an example outcome that could occur if the null hypothesis were true, meaning that there's nothing happening here other than random chance. Which section you're in has no effect on your midterm score. So let me suggest a way that we could get that. We have the distribution of scores. And we could now, let's see, how many students were there in section 3? We could sample a new simulated section 3. There were 27 students in section 3. So we could sample a simulated section 3 by, what was the randomness here? The randomness was, I guess, assignment of students to sections. We could come up with a new random assignment of students to sections where we pick 27 people from the class as a whole, and we assign them to this simulated new virtual section 3 in my imaginary universe where the null hypothesis is true. And that will give me some example scores that could occur. Well, I guess I only want the scores. There are scores that could occur from a simulated virtual section 3 if the null hypothesis is true. And there's another sample, another example. And I guess what I really wanted was the value of the test statistic. So let me show you how to compute the test statistic. Right. So the test statistic is just the average of those scores. And that this time our simulated, in our simulation, our simulated section had an average score of 15.37. I could do another simulation, and that time they got 14.18. All right, so you can see that each time I do the simulation, each time I do a new random assignment, I get a new value of the test statistic. And there'll be some range of values that you could get. Here's another one, 15.44. Here's another one, 16.0. So you're starting to get a sense for what range of values of the test statistic would be normal if the null hypothesis were true. But let's make that a little bit more systematic. What we're going to do is we're now going to simulate many times and look at what the distribution of those values are. Okay, so to help us, we're going to take what we just did and we're going to put that into a function. And what this function is going to do, this is going to be a function that I write that does one simulation. So it simulates the process of doing one random assignment of students to sections and looking at their scores and computing the test statistic for that simulated sample. All right, so I just took the code that I just wrote and I put it in a function. Ta-da! And now I can look at a simulated outcome, the value of the test statistic for a single simulated outcome by running this function once. And if I run it multiple times, I'll get multiple different answers. With replacement equals false means that I pick 27 students, and I don't pick any student twice, because when you assign to sections, you never assign like a student. Each student gets assigned to a section, and then so you could think of picking who's in section 3 by picking at random one of the 360 students, and then that's the first of the 27, and then picking at random another of the 360 students. That's the second person in the section. Well, I want to be careful to make sure that I'm not picking the same student twice. The second student I pick should be different from the first student I pick. So that's what we mean by without replacement. After I pick the first student from the 360, I don't put them back into the pool to be picked. They're already assigned. So now I'm only picking from the next 359 students who haven't yet been assigned. Okay, so that's not super important. That's kind of a little detail. That's a little bit of a distraction. If you didn't follow that, no big deal. That's not the main point of what I wanted you to get from this lecture. All right, so now I know how to do one simulation. Well, computers are great. Anything you can do once with a computer, you can do lots of times. So let's do that. Let's do this simulation many times and see what range of values we might plausibly get. And so I'm going to store all the values. I'm going to do 50,000 simulations. And I'm going to store the test statistic that was gotten from each one of those simulations into an array. So each time I execute this for loop, I'm going to do one simulation, and then I'm going to append it, that result that I got, this test statistic that I got, to the array. And it would help if I remembered my syntax for loops. All right, and I'm going to run that, and the computer's going to take a little while and do 50,000 simulations. And then I can look at the values. So there's a whole bunch of values. Those are simulated values of the test statistic that were simulated using the assumption that the null hypothesis is true. That there's nothing happening here other than chance, that really section 3 is not, there's nothing different about section 3. They just got unlucky on the midterm. All right, so now I'm going to visualize the predictions. These are the predicted values, and I'm going to form the empirical distribution, and I'm going to visualize that. So let's put this in a table so I can use my histogram method. Okay. I'm going to draw a histogram, and there's a histogram of the values of the test statistic that you might see if the null hypothesis is true. It's a distribution because that depends on the random choices that were made in assigning students to sections. All right, so you can see here from this simulation that it's not unusual to get values like 15, 16, 14. Those are fairly likely values to get for this test statistic. In other words, for the average in that section. Whereas a value like 20, very unlikely to get if the null hypothesis is true. So now let's add in the observed value of the test statistic. And don't worry about this code. I'm just doing some code here to just draw it on the visualization. You don't need to know how to do this. Well, shoot. No, of course that's not defined because I didn't assign it. Here was the value, 13.6667. Okay. So the observed value of the test statistic was 13.667. I'm going to draw a histogram. So the blue dots represent the prediction. There's what happens if the null hypothesis is true. The red dot represents the observation. So now we can ask ourselves, is this observation appear to be consistent with the predictions from the null hypothesis? What do you think? Type me in chat what you think. Nice. I love it. I love the answers. I see a bunch of yeses. I see a fair number of no's. I see a few plausibles. It's hard to tell. Not enough to tell. Possible but unlikely. Reasonable but unclear. Yeah, it's kind of a little murky, right? If this red dot fell like over here, I would say, sure, that could totally happen. That's totally plausible. If this red dot fell all the way over here, I'd say, no way. That's a super, super unlikely. I would have to believe in an extraordinary coincidence to believe in the null. But here, it's like a little bit unlikely, but maybe not super unlikely. How unlikely is it exactly? How should I use this to make a decision? It looks a little bit fishy, but maybe not clear cut. So, all right, this is why we need a procedure. And this is where I want to teach you about the notion of statistical significance. All right. So here what we're going to do is we're going to now systematize the procedure we were using before. In the examples we looked at before with the Alabama jury, we had the blue distribution of predicted values, and the observed number was way outside the range of what you would expect to see from if the null were true. So we were very easily able to reject the null. The Alameda situation, again, the observed value was way outside the range of what you would expect to see if the null were true. So we're very easily able to reject the null by just looking at the visualization. With pea plants, the observed value was clearly within the distribution range of plausible values. So we couldn't reject the null. It looked like the null could well be correct. But now we're in a situation where it's not quite so clear cut. It's not clearly outside, not clearly inside. All right. So we need a way to measure just how unlikely is this occurrence. All right. So we're going to do that by looking at how far it is on the side towards the tail of this distribution. What do I mean by a tail? The tails are these regions on the ends of the distribution where it's very small. Those are called the tails. All right. So if the test statistic is in the tail of that distribution, then that would tend to suggest that the null hypothesis is wrong, and we say it's inconsistent. The observed value is inconsistent with the null. How far out before we declare it inconsistent? Well, here is where there is no hard and fast answer. And so there's just a convention that's arbitrary. It's arbitrary. It's made up. Someone made this up and said, this is the rule I'm going to use. There's no reason you have to follow this rule too. It's just a convention. It's kind of an arbitrary convention. They say if the area in the tail is less than 5%, if it's so far out into the tail that the amount of the tail on that side is less than 5%, then I'm going to declare it to be inconsistent. And if it's not that far out, then I'm going to declare it to be consistent. All right. So if it's less than 5%, I'm going to call this statistically significant. There's another convention that's out there that some people use instead of 5%. They say 1%. So what's the meaning of this? The meaning of this is the first group of people say, if I would have to believe in a coincidence that happens less than 5% of the time to believe in the null hypothesis, then I'm going to say I kind of no longer really buy into the null. I'm going to say these results are statistically significant and I'm rejecting the null. And the second group of people say, well, I'm a little more cautious. I'm not willing to reject the null in that case, but if it would believing in the null would require me to believe that what just happened was a coincidence that would happen only 1% of the time, in that case, that's too much of a coincidence for me, and then I'm rejecting the null. Okay, so this is about measuring how unlikely, how much of a coincidence do you have to believe in if you want to believe in the null. And we call this measure the p-value. So let me tell you what the p-value is, and then we'll call it a close for today. So here we have a distribution of the predicted values under the null. The red dot represents the observation. And then what we do is we kind of draw a vertical line around that observed value, and we look at all of the values that are to the left of that. If you saw that value, or you saw a value that was even more extreme, all of those are more suggestive of the alternative hypothesis. And you look at how likely is it, if the null were true, to get a value that's 13.67 or lower. And the likelihood of that is obtained by taking the area of the yellow part of that curve, the area of the tail to the left of the red dot. We compute that area. That's called the p-value. All right. So now it could be that if the null were true, that you could get a value that's 13.67 or lower. That could happen. It would take a little bit of a coincidence. How much of a coincidence? Well, the probability of that happening is measured by that yellow area. Okay, so we call that yellow area the p-value. That p-value is a measure of how unlikely or implausible is the observation. A smaller value is more implausible to have happened from the null. Smaller values are less consistent with the null. Larger values are more consistent with the null. And the decision rule we're going to use is if that value is too low, then then we reject the null hypothesis. So the first group of people I told you would say, if the p-value is below 0.05, then I reject the null, because the only way the null would be true is if what happened amounted to something that is a coincidence that would only happen 5% of the time. And they say, I don't think that coincidence is very likely. I think it's more likely that the null is false. All right. So that's the p-value. We're going to spend a little more time on this on Friday. And don't forget to do your homework and your vitamin. Homework due tomorrow and vitamin due Friday. Come join me in my office hours right after lecture if you would like. Thank you, everyone.